We have been discussing so much about constrained random coverage driven verification and test bench architecture. Now it's time for us to understand the realistic verification process that we follow in the industry. In reality, actually we do multiple things to verify the RTL. We do rule checking, we do assertion-based verification, we generate different kinds of coverages like functional coverage and code coverage to track the simulation progress. Basically, we do multiple things to gain more confidence, and that's how we want to sign up the verification process and move on with synthesis. Look at this. We have created the system Verilog test bench. It does random simulation. But the test bench, what it does is data integrity checking. What it means is the scoreboard that we have implemented as part of the test bench, it compares the packets. It collects the DUT output and it compares the output packets with the reference packets. It's called data integrity checking. But we also need to verify the protocol. If you look at the DUT, obviously there will be different kinds of interfaces, and in reality we use different kinds of standard protocols like AXI, AHB, SPI. When it comes to protocols, we have to verify the protocol also, how the data flow happens. That's where we need to go for temporal checking. We need to verify the data flow in terms of clock cycles. That's where we apply methodologies like assertion-based verification. In addition to assertion-based verification, we also need to generate different kinds of coverages like functional coverage and code coverage. That's where you need to understand the difference between functional coverage and code coverage, and how to make use of all the coverage information to sign off the verification process. That's what I'm going to explain in this chapter. All right. Linting. It's nothing but rule checking. Basically, it's a static verification. What it means is we don't write any test bench and do simulation for rule checking. The tool is going to do everything. That's why it's called static verification. Here, if you look at the flow, we feed the RTL source code to the tool, and the tool has been built with different kinds of rules. There will be different kinds of standard rules. And based on the rules, the tool is going to compile the source code and check whether there are any violations with respect to naming conventions and coding style. Basically, we use lint tool to enforce naming conventions and coding style. For example, you are working for an IP vendor. Then the company might enforce certain naming conventions and coding style. That's highly needed for the products like IPs, because when it comes to IPs, we have to take care of the reusability of source code. Also, when it comes to selling the IP to the chip maker, we have to convince the chip maker with all the information like how we follow naming conventions and coding style within our organization. So, naming conventions and coding styles are highly needed to improve the quality of the source code. That's what we do with the lint tool. So here, the tool is with different kinds of rules. There may be a lot of standard rules. In some cases, we might want to customize the rules also based on the requirements of the organization. For example, I'm working at Maven Silicon, and within Maven Silicon, I want to follow certain naming conventions. Also, this kind of lint checking is required when it comes to dealing with inexperienced designers. Someone is not experienced, but the person is really good at implementing the logic like RTL source code. Then while writing source code, what are the things basically the designer has to take care? For example, if the person is planning to use if-else, then how many nested ifs he can have, how many levels he can go up to. It could be 5, it could be 10. Suppose he is going to increase the nested ifs up to 10. Then the challenge would be simulation debugging. Later on, when it comes to finding bugs, and if there could be so many nested ifs, it would be really difficult. That's why we always make sure that we follow coding style. So we feed the RTL source code to the lint tool, and the tool is going to compile the source code based on the rules, and if it finds any violations with respect to naming conventions and coding style, it's going to report the error. And once the designer finds the error, then he is going to clean up the source code. In some cases, it could be even design issues also. For example, we would be able to find the issues like combinational loops or multiple driven signals. So we can define rule in such a way that we would be able to identify some of the basic design issues. We can follow coding style for RTL. We can also follow coding style even for the test bench. For example, when it comes to system Verilog test bench, we want to follow the standard methodology like IEEE based UVM. When it comes to UVM, we may need to follow certain coding styles. That's what we can achieve through linting. All right. Code coverage. The big question is my TB good enough to execute the complete RTL? Or I would say, how can I measure the quality of my test bench? I have questions like whether my test bench is good, or whether my test bench is okay, or whether my test bench is not okay. If someone is asking me like, what about the quality of your test case? Can I take all your test cases? Or how I would be able to rate my test cases? I have written multiple test cases, but I want to identify which are all the test cases highly productive, which are all the test cases redundant, which are all the test cases useless. So after writing so many test cases, I want to do this analysis and I want to optimize my test weight. How can I do that? That's where code coverage becomes critical. Basically, we use code coverage to improve the quality of test case or the quality of test bench. Look at here: statement coverage, branch, expression, toggle, FSM. When I say statement, we check whether we can execute all the statements within RTL, whether all the statements have been executed. Let's say there are 100 statements. Then the question is, out of 100 statements within RTL, how many statements have been executed? Whether all the statements are executable statements, or some of them could be comments, some of them could be redundant. We would be able to identify even redundant logic lying in the RTL code. We have implemented the functionality. Sometimes there could be redundant code lying. In that case, the code coverage will always be less than 100%. When you get less code coverage, then you are there to ask question. My test bench is working fine, I'm getting the functionality, but why the code coverage is less than 100%? That's where you will come to know there is some kind of redundant logic. The designer has written some kind of unwanted logic, and that's lying. And that's going to be unnecessary logic. That's going to be additional gates during synthesis. So we can clean up the RTL code in that way. So we can check how many statements have been executed. The same thing can be applied for branch coverage. If you are going to have if-else or case statements, then the question is, have we executed all the branches? Suppose it's going to be like if, else if, else if, else if, then we need to check whether all possibilities have been covered. That's highly required for statements like case. And then expression coverage. Expression is nothing but condition coverage. If you are going to implement conditions, then we need to look at what could be the possibility. How many possibilities would be there? Then toggle coverage. Let's say there is some kind of shift register or counter, then how all the bits are going to toggle. How many possibilities are there? And what about the switching transitions? If the transitions are going to be more, then obviously that's kind of indication that it's going to consume more power. When it comes to finite state machine, we look at various things like state, transition, and path coverage. You have written RTL code for finite state machine. Then when you apply code coverage, the simulator can extract the finite state machine from your source code. So you would be able to see the schematic, like how many states will be there, how many transitions will be there, what kind of possible state sequences would be there. All those things can be analyzed through finite state machine coverage. So this code coverage is generated by simulator. We don't really need to write any source code. During simulation, when you activate the code coverage option, obviously the simulator is going to generate all kinds of coverage information. You would be able to even choose the metrics also, whether you want to generate statement or branch, or you want all kinds of coverages. All right. Look at this example. Sometimes it helps you to find the design issues also. For example, you have written if, else. Here the condition is A and B. Actually we used logical AND instead of OR. This is the expected one. So this is bug. And if you consider this if else, there are two possibilities. One is executing true logic, the other one is executing false logic. So when we implement this kind of logic, obviously we would look at like how to execute true logic, how to execute false logic. So we always try to apply the pattern 0, 0 and 1, 1. When we apply 1, 1, it becomes true, it executes true logic. When we apply 0, 0, it becomes false, it executes false logic. Here the big question is, how can we differentiate OR from AND? If you look at the patterns, when you apply 0, 0, it becomes false for both OR and AND. When you apply 1, 1, it becomes true for both OR and AND. So obviously there is no difference between the logical operators OR and AND, especially for these patterns. That's where when you apply expression coverage, the tool is going to look at the expression. In this case there are two variables, so obviously it will try for all possibilities. 2 to the power 2, 4 possibilities. Here we are generating only 2 patterns, so the coverage is going to be only 50%. 0, 0 and 1, 1, only 2 patterns, so the expression coverage is going to be 50%. When we try to improve this coverage from 50 to 100%, obviously we would think of generating the other patterns. That's 1, 1 and 1, 0. When we try these patterns, obviously we would be able to identify this bug. We will come to know that we have used logical AND instead of logical OR. That's how expression coverage works. Functional coverage. We have been discussing so much about constrained random coverage driven verification. Simply speaking, coverage driven verification. So for random simulation, what is really needed is functional coverage. With the help of functional coverage, we would be able to measure the quality of design verification. So this coverage is used to measure the quality of design verification. So there are questions like, have we verified all the design features? Have we generated all the test scenarios? How can we measure the progress of verification? We have been running simulation. So the question is, how much more time it's going to take for the verification sign off? When are we going to complete? How much we have done with the simulation? Have we covered 60% or 70% or 80%? How much more is pending? So to track the simulation progress, we make use of functional coverage. Functional coverage is mainly used to verify the design functionality. Here, look at this example. This is DUT. It's a router. We discussed about this router. It has got input channel and multiple output channel. So here we can define the coverage in terms of packets and channel. There are two things here. One is packet, the other one is channel. I'm going to define packets like small packet, medium packet, big packet and corrupt packet. There are 3 channels, channel 0, channel 1, channel 2. They are all output channel. If I'm going to get all these kinds of packets, through all the channels, I would be able to confirm that the router works fine because I have tried all possibilities. When it comes to packet, there are 4 main possibilities I'm looking at. One is small, the other one is medium packet, big packet, and corrupt packet. So in my view, if I can send all these packets to the router, if the router can direct or route the packets to all the output channels, then I would be able to confirm that the design works fine. That's why I want to try all these combinations. So if I am going to achieve 100% coverage for this particular coverage model, then I would be able to sign off the verification process. That's how the coverage works. This is functional coverage. Here we are not checking whether we are executing every statement of the RTL code, whether we are executing every branch. That's code coverage. So to understand precisely the code coverage and functional coverage, you need to understand the difference between code and functional coverage. Look at here. Code coverage, it's generated by simulator. It's an automated process. We don't really need to write any source code. But when it comes to generating functional coverage, we have to implement the coverage model in System Verilog. So it demands coverage model. It's a manual process. And code coverage measures the quality of the test case. So with the help of code coverage, we would be able to rate the test case, whether the test case is highly productive or redundant or less productive. We can use functional coverage to measure the quality of the DUT verification, how much we have covered. And code coverage checks whether RTL source code has been executed completely. Functionally, how it works, the code coverage verifies whether every statement has been executed, whether every branch has been executed, whether every state has been executed. And functional coverage verifies whether all the features have been implemented properly. So it's meant for verifying the design features. If there is a router, then the question is whether it can handle small packet, whether it can handle big packet, whether it can handle medium packet. That's what we try to verify. And code coverage generated directly from the RTL source code. You have written the RTL, there is a test bench. While running simulation, you apply code coverage. The simulator is going to generate code coverage directly from the RTL source code. We don't apply generally code coverage for the test bench. And functional coverage generated mostly from the stimulus. So from where we are getting functional coverage? Mostly from the stimulus, the kind of packets we generate or the kind of frames we generate. In case of router, the packets could be small packet, medium packet, big packet, corrupt packet. That's nothing but functional coverage. And we can also use code coverage to measure the switching activity. If we want to calculate the power consumption during switching transitions, then we can apply code coverage and measure the activity, switching transitions. And functional coverage can also be used to measure the test scenarios coverage. Not only for design features, you can also define test scenarios. For example, we can look at like if we are going to apply the sequence of packets like 10 small packets, 2 big packets and 1 corrupt packet. If we are going to apply this sequence, then what would happen to router? This is called test scenario. We can also define such scenarios through functional coverage. All right. Assertion-based verification. Look at here. This is the System Verilog test bench we have written, and this is DUV, design under verification. In this case, it's an SOC. So this SOC has got multiple IPs, and all the IPs have been connected through on-chip bus. So it's a complex chip. During simulation, it happens like black box verification. What it means? Here we apply stimulus, all the values will be given to DUT, When the DUT produces output, we always look at the output. Mostly we cannot understand anything what is happening inside the DUT. This is called black box verification. And in this case, simulation debugging will always be time consuming. For example, when we identify any simulation mismatch, then we have to do back tracing, and then we need to identify which logic is creating this problem, and that's going to be time consuming. In that case, if we add assertions within RTL, these assertions could be like probes, monitors, and whenever anything goes wrong within IP or within subsystem or within module, the particular assertion will highlight, it will report the error message. So here there are assertions embedded within RTL. We can also add assertions for the interfaces, and in this case, let's say we apply the stimulus and then we get the output. There are some simulation mismatches. At the same time, we get error message from a particular assertion. So we can correlate this particular data mismatch with the assertion error. We are also getting error from the DUT. At the same time, there is an error message from a particular assertion. So we would be able to identify the exact module. This is the particular IP. Within this particular IP, we have written some assertions for a particular component like decoder, and this decoder is not working properly. That's why we are getting this data mismatch. You are running simulation. At the output, you are getting error. At the same time, within DUT, there are some assertions failing. So you would be able to identify exactly which component in which IP is creating the issue. And the simulation debugging is going to be very easy. This is called white box verification. We also use assertion-based verification to verify the protocol. When it comes to protocol verification, we want to verify everything in terms of clock cycles. That's where we apply temporal checking. And generally for assertion-based verification, there are two kinds of technologies available. One is static ABV, that's primarily used for verifying the functionality, and the other one is dynamic ABV. That can be used for both protocol validation and functionality verification, and that can be applied at any level, IP level or SOC level. The static ABV is automated one. Basically, we use the tool to verify the RTL. So we need to write the RTL, and then for the RTL we need to write all kinds of assertions, and then we feed both RTL and assertions to the tool. The tool is going to verify the functionality based on the assertion. That's called static ABV. But that doesn't work fine at SOC level because the design complexity is more. Obviously, the tool is going to consume so much time. But the advantage of static ABV is coverage will always be more because it's kind of completely automated process. So when you feed both RTL and assertion, the tool will try all possibilities to verify the functionality. So the quality of verification is more with respect to dynamic ABV. The dynamic ABV is based on the standard simulation flow. We need to write test bench. In addition to test bench, we also need to write assertions for the interfaces. Also, we can embed the assertions within RTL. So there are two ways how we add the assertions into the design. One is we write assertions as embedded assertions. So basically, we write assertions as part of the RTL itself, like comments. The other way, we add assertions in a separate module and then we connect the module through a bind construct. So that's kind of assertion unit. Look at this example. This is one best example for protocol validation. Property, handshake, end property. At every clock edge, it's going to verify this protocol. If there is any rec in the next clock cycle, that should be acknowledged. So if rec is going to be high, in the next clock cycle, act should be high. That's what it means. That's what we try to verify through this property, handshake. This is how assertion-based verification works. All right. In this module, we discussed about constrained random coverage driven verification. How basically we write system verilog test bench and run random simulation. Also, we discussed about verification plan, how this V plan is different from test plan, and how we make use of this verification plan for the verification sign off. So usually the project manager is the one who defines the verification plan and eventually is going to look at the coverage closure, and based on the coverage closure is going to sign off the verification process, and then is going to approve the design for synthesis. And based on the verification plan, especially the test bench architecture, the test bench developers, they implement the test bench, reusable test bench, and the test case writers, they are going to make use of this reusable test bench and write all kinds of test cases. So these test case writers, they will come up with different kinds of random test cases, and they are going to run all the test cases and generate different kinds of coverages. When it comes to coverage, yes, we will look at different kinds of coverages like functional coverage and code coverage, and from all the test cases we generate coverages like functional coverage, code coverage, even coverage from assertions also, and then we merge all the coverage information. That's how we are going to generate final coverage report, and project manager is the one who is going to look at the final coverage. If the coverage meets his expectation, he is going to sign off the verification. Also, in addition to the random simulation, we do various things like rule checking, which is nothing but linting, and we also apply assertion-based verification to verify the protocol, and we deal with different kinds of coverages like code coverage and functional coverage. All right. Hope you enjoyed this video. Thank you.